Okay, so today the sort of the Excel, what do I want to say, intro course in Excel, and we're going to use the energy equations that we've been developing and talking about thermodynamically as equations that we can plot in Excel. Okay, so we've already done sort of the partition function for rotational energy. Remember that? That's what we did, and we did solve that also for the maximum and related it to temperature. But it was the J quantum number, and it was for rotation. And we had this B, this rotational constant. And we didn't really explain what that was. I just gave you what B was for HCl and carbon monoxide and carbon dioxide. Do you remember that? So this is B. Okay. And so this is for a diatomic only. Okay. And you have this mu r squared in the denominator. This is the reduced mass. So for the diatomic, you have the two atoms, their masses, and that's how you come up with reduced mass. And then R is the bond length between those two atoms. So this is the rotational constant. The others are just constants. You have the speed of light, pi, and Planck's constant. And so this, if you know the mass of both atoms, and you know the bond length, then you can calculate the rotational energies. Okay. What about the translational energies? This had the quantum number n. This was a particle in a box problem. We'll just talk about one dimension. So we'll just say that this particle is going along the x-axis. And so that's going to be n squared h squared over 8ml squared. And so this L is the length of the box, so it's confined to a particular region. This is the mass of the particle, and the quantum number is in the numerator, and it's squared. And then finally we have vibration. And this has a quantum number V. And it's typically written with the vibrational frequency and wave numbers. So that would be nu tilde. Actually, let me go ahead and put a tilde on this B here too. Okay? Because that'll indicate that it's in wave numbers. That's what that little thing means. Okay? Now this equation can be confusing to some, and it's a common mistake, to get this V confused with the Greek character nu. Okay? Especially when it's typewritten, because sometimes in certain fonts, they really are close together. So you don't know if it's talking about V, the vibrational quantum number, or nu, the vibrational frequency. Okay, but in context, you should be able to figure it out. But if you're just sort of looking at a character in text, sometimes it's difficult to tell the difference between a V and a nu. The tilde would help. Okay, so if it's nu tilde, you'll know it's not the vibrational quantum number. But I just always like to try to point out the things that some people get confused on when they're reading. Now this vibrational frequency also depends upon mass. there's some constants out front, but it's in general the force constant over the reduced mass of the two bodies that are oscillating. Okay, so like for a diatomic, it's just that bond stretch, and you have the two masses. Again, the reduced mass is calculated with the two masses, and then this K is the force constant. And it's very similar to a spring constant. So when you did physics back in the day, and you had Hooke's law, the potential energy was minus 1/2 kx squared. So as you stretched x, the potential energy went up with the square of x. The force that you were having to pull against was this force constant for that spring. So you had a really stiff steel spring, it was really hard to pull, and you had a very steep curve. If it was a really floppy spring, a tiny little wire spring, then it was very easy to pull and you had a very shallow potential. Same thing for molecules. So we actually can treat molecules like two masses held together by a spring. It's called a harmonic oscillator model for vibration. And it works. It's amazing how well it works. That you can just treat the atoms like balls on a spring, and you can use this force constant. And so what would be a tight spring would be something like a triple bond in acetylene or in nitrogen. So very tight, a very large force constant. A very weak force constant would be a single bond. Okay, so between fluorine. So just a single bond between two fluorine atoms, it's going to have a lower vibrational frequency because the spring constant or the force constant is smaller, so the vibrational frequency would be smaller. If the spring constant for like a triple bond is higher, then your vibrational frequency is going to go up. Okay. Before I move on, is anything sparked your curiosity? Any questions about these energy equations? Okay, well then I'm going to switch gears and I'm going to put Excel up here and we're going to plot these different ones, okay? And I want to highlight which ones are quadratic in quantum number, which ones are linear in quantum number, and those kinds of things. So let's do that. So go ahead and open up Excel on your laptops. And so what I would like to do, let's just divide and conquer, okay? So let's break the group up into three. So let's have you four do the rotational energy equation, okay? And then you four here do the translational energy, and then you three do the vibrational, okay? And y'all can talk to each other if you need help. And so what we're going to do is we're going to set up a column of quantum numbers, and then we're going to calculate those energies. Now in terms of the constants, I'll have to help you out with the constants, and we'll put those on here as well. But like what's a reasonable vibrational frequency to use, what's a reasonable rotational constant to use, and so on. Now we can go all the way down to the reduced mass there. Let's go ahead and do that. And actually you can also use the internet to find, say, the force constant for a particular single bond or something like that. So using the internet, using masses from the periodic table, let's go ahead and compute these three energy equations, and let's have a column of quantum numbers and then a column of energies, okay? And so this will also help you help each other to learn Excel. So what I like to do is put my constants up top. Let me make this big so that you can actually see what's going on.
Oh, so 1, 2, 3?
Yes.
Okay.
Yeah, and so y'all are working on vibrational energy. So y'all will look up a force constant, agree on a molecule, and so then you know what masses to use and the force constant.
H and or yeah. I'm just typing out some questions first. So it's like 5. Okay, thanks. Oh, we can like change technology. Interesting. Yeah, never mind. So that's nice. So it's kind of on the right. So it's like I just have that page for a bit. So what means yeah.
And if you have any questions, ask right away because we don't have much time.
Translational.
Pardon?
And translational.
Yes.
The fact that it actually is independent variable.
Yeah.
Is it the N?
Here's what we'll do. Let's all do carbon monoxide. Okay? So everybody, let's just do carbon monoxide, carbon 12, oxygen 16. And that way we know what masses we're dealing with, what vibrational bonds we're dealing with, and for translation, you know the total mass. Does that help?
Yes.
Yeah, okay. I want everybody to look up real quick. Notice, like for Planck's constant, look how I entered that. So if I type in 6.626 E minus 34, that's the scientific notation way to enter. So when I hit that, then it knows that that's what that means, okay? So you don't have to do times 10 raised to the power of minus 34, which I see sometimes when people are learning Excel. And so this is just a way to enter scientific notation, okay? What box length do you want to use, guys, for the, okay. You said 10 angstroms?
Yes.
Okay. Here's an interesting thing about the quantum numbers. The translational quantum numbers start at 1, but the rotational quantum numbers start at 0. Okay? And the vibrational quantum numbers start at 0. Okay? So J equals 0 is a valid quantum number, but N equals 0 is not a valid quantum number. Okay. Now I'm doing all three. Y'all don't have to do all three. So I'm just letting you know. For the purposes of our class and just being quick, let's just call carbon 12 12 and oxygen 16 16. So instead of decimal places, let's just do that. So 28 is the mass total. I'm just putting a lot of my constants up top. It'll help me when I do the formulas. Say again?
No, I'm just thinking out loud.
Okay.
So H is N is unitless, right?
Say again?
N is unitless.
Yes, all the quantum numbers are unitless.
No, I can't make it so it's not or there's
Yes?
I'm kind of confused what we're doing right now. I'm not exactly sure what we're supposed to be doing.
Okay, good question. You guys are vibration, so you have your vibrational quantum numbers, and you are going to enter in the energies of those. So you're just typing in this energy equation, so you need to look up the force constant for carbon monoxide and compute the reduced mass. Yeah, and then there's some constants out front here that you'll need to get it into wave numbers. Okay, so that's what you're doing. And it's just an introduction into Excel, but then at the end we're going to talk about the comparison between these different energy equations, that they're really on different scales. Yeah, so that's why we're kind of in a hurry in terms of trying to get the energy equations done. Yeah.
I think the problem is
I'm doing my masses in kilograms.
yeah, that makes sense.
And so to get out of grams per mole, you divide by Avogadro's number and then divide by 1,000. So you're going from grams to kilograms.
No, unless you want it in thermal six, which is fine, right?
Yeah, if you want to use, I mean, you'll convert it later someplace else, right?
So it's
But with the Planck's constant, you're going to end up with joules, and that has a kilogram in it. So. Okay, let me show you, everybody, if you can get your eyes up here. Notice on the screen, I'm starting to enter this equation here. So I'm starting to enter the translation equation. I have n squared. So my n column is here. So I have n, A9 is my first n, caret 2, so that's n squared, times, and then I'm using my cell for Planck's constant up there at the top. See, it's color-coded, it's red. But I have to hit F4 to anchor it to that cell. Because when I copy this down, I don't want the reference to move. because on this cell it would refer to the speed of light, and then on this cell it would refer to the speed of light in centimeters. Okay, I don't want it to follow me down. When I copy this cell down, I want the formula to update in, but not H. I want H to stay there. So these dollar signs are anchoring the column, and this dollar sign anchors the row. Now you can type those in, or you can click up there and hit F4. And when you click F4, it anchors both. If you click it again, it anchors just the column. You click it again, it anchors just the row. Click it a fourth time, and it goes back to not anchored at all. So you can just cycle through F4 until you get the dollar signs you want. Okay, so that's a key skill in Excel that if you've not used Excel much, then you don't know that. And so this is an important part of today's lesson, is to learn how to anchor cells. Okay. Let me show you also Excel. You can get crazy with parentheses and make life difficult. Okay, and so I've got n squared times h squared divided by 8 divided by m divided by l squared. You don't need parentheses. If it's just multiplication and division, you can do this in any order. In fact, I could have said n squared divided by 8 times h makes constant. You can do it in any order, because division and multiplication are commutative.
I like to sing my formula.
Yeah, so. Okay.
I got 1.18, but I had the wrong key.
Really?
So I got something messed up.
Let me see. Meters, kilograms. This is in joules. Okay.
Not seeing any difference. Yes. Yeah, that's what I have to mess too.
Here's my formula.
E6, what the freak? Why did it be 6?
Say again?
I messed up.
Okay.
Why is that E6?
For my automotive number up to negative 23.
There we go, I'm good.
Okay.
It's an L06. So we can do.
I'd like to convert that energy over to wave numbers so that we can compare everything in wave numbers. So E over HC should be wave numbers.
Do we lose them all, right?
Divided by Planck's constant again, so that kind of cancels one of them. And then divided by C in centimeters will give us wave numbers.
So let's do this tonight. Right, this break. Divided by this. Divided by this. Yay.
You got the same? Good.
Yes.
Makes me feel
Oh,
good.
I didn't anchor. And then yes. I just tried
Looks
to
like
count.
my anchors are holding. Good. Now those are, who's doing rotation? Y'all are doing rotation? Okay. And you put in This equation, what did you use for the bond length of carbon monoxide? Okay. Did you calculate B in wave numbers already? Not yet? Okay, okay. I think it's 1.93, but I'm not sure. I'm just gonna kind of.
It's divided by 8. Make sure it's divided.
What did y'all get for the vibrational frequency for carbon monoxide? You haven't found it yet? Okay.
Oh, yeah.
Since we're, let's, for the sake of time, let's just look that up. Instead of calculating the force constant and the reduced mass, let's just look up the vibrational frequency. And the same, if y'all are having, if the rotational constant is slowing you down, just look it up. I think it's 1.93 from our previous notes, but let me just go there real quick. Okay, it's looks like it's like 21, I'll say 2140. 2140. Okay, that's close enough for our purposes. It's right here in the middle. Okay, and so for the rotational constant, it's 1.93 wave numbers. Okay, does that help? Yeah. Yes.
Oh yeah, I think just grab that. And that was the one.
What's wrong, Will?
That's it. That's gonna be the one for.
Yeah, that helps to get to wave numbers real easily. That's why I put both so that you would see what I was doing. Meters on top, centimeters on bottom. Yeah.
What I do? How many use any? Let me see. What? 40. Oh, same thing. No, I think 30. Less. And then
What's that?
lock it so it's
Yes. Yes. And so here's the 3 columns that down here at the bottom. So this is the particle in the box. The translation, here's the rotation, and here's the vibration.
And then your E5 should be your length squared. So you go to this one, E5, and then square it. That should be good. So there's an oh, you didn't put the equal sign from very right.
helps me find it.
I like that one. I do that to my computer.
It helps me find where the stinking mouse is. I got two screens, and so I've got to shake it like crazy. Oh, there it is.
I will say, like Max tells us that if you shake it, the arrow gets big.
Oh, that's nice. Still not going to get a Mac.
The only reason I know the reason for that.
Yeah. Okay, that ain't right. Okay. Okay, there you go.
So if you're going to plot on the same plot, you're going to have to change the 0 to 1.
We'll see. Okay. Yeah, got it.
Well, you made me happy.
Yeah.
So in your format, you say, so when you select edit, you say -1.
What are you talking about?
It's no preference that way. Is that value, the value for that that cell -1? Where's the sheet?
Up here,
Yeah.
it just says E8 to E11, F8 to F11. So it's got them lined up. Yeah. Okay, so we've got about 10 minutes left. Did everybody get to the point where they were able to compute their columns of energies? Okay. Did y'all get the columns of energies, the rotational column? You should have this column right here, this theta here. You have that? Yes. Okay. I'd like to show two things here. First of all, I'd like to show that thermodynamically, because that's this course, right? There's a huge difference between vibrational energy and how we can store energy in vibrations, and then rotations and translations. I've plotted all of them on the same graph here. And yet I only see one set of bars, right? And so it's kind of an interesting thing to think about. If you plot it on the same graph and you can't see it, it really doesn't interact, right? Things of similar energy, and another way to think about it is, if energy levels are close to each other, then they can interact. If they're not close to each other, they just don't interact. So the rotational motion is going to be pretty much the same whether it's in the ground vibrational state or the excited vibrational state. Because the molecule is rotating, it really doesn't know that it's vibrating. And the molecule that's vibrating really doesn't know that it's rotating. Those are so far apart in energy that they're independent of each other. Nearly completely independent. There is some vibration-rotation coupling, but it's a really small effect. So this is sort of separating our ideas in translation, vibration, and rotational motion in molecules. And I just wanted to have a graphical display of how different they are. So I'm going to delete this series. I'm going to copy this. Actually, let me just copy this graph by control dragging. So look, I'm dragging with the control key down. And then when I let go, I've got a copy of the graph. So that's a nice little trick. Okay, now we have translation and rotation on the same graph. And we can see that they're similar. I mean, they can see them on the same graph, but again, pretty different. So there's very little interaction between rotation and translation. But there, at least here, there's you can see them. You can see the translational energy levels for carbon monoxide. And so then, dragging this again, now delete the rotation, and here's our translation. So everything under 1 wave number. I mean, it's, you know, we're in the second excited state, and we're still not up to 1 wave number of energy. So we're doing our 2-level system or 3-level system. We were talking about 100 wave numbers, 200 wave. We have 200 wave numbers at room temperature. And translational motion, I mean, here we have 3 quantum states. It's excited, and it's still not even up to 1 wave number. How many populated levels do you think you have at room temperature for translational motion? A lot. Okay, so you could calculate that, and essentially that is the partition function. Taking 200 wave numbers and dividing it by the energy between those things, you'll get the total number of levels that are populated.
It's kind of like almost backwards, like, I guess it's like, it's not, when I think of like movement for gas in like a room,
Mm-hmm.
it's like a lot of movement so that you could see like a large number, right? Or no? Like,
A large number of what?
for the energy that it could, or that it needs to, I don't know, I guess move. Because that's the translational motion, right?
Yeah, translational motion, but it doesn't take really any energy to get a molecule moving because there's no resistance force. The only thing resisting getting that particle moving is its tiny, tiny mass. Whereas to vibrate, you have to pull against that spring. What's holding those 2 atoms together is the electron cloud and the positives and negative charges. And positive and negative charges are pretty strong. So pulling atoms apart, you're fighting Coulombic charge. And so that's got a huge energy barrier. Yeah. And it's surprising to me that rotation's not easier than it is. But for a larger molecule, it's the rotational constant's really small, so you can excite it more. Notice another thing that's an interesting point. Yeah, 4 minutes. So where is mass in all of these? In all of these equations? Let me flip this. Mass is in the denominator in all these equations. So what happens to the energy level spacing when the mass gets big? It crushes down, okay? And so this is what's called the correspondence principle of quantum mechanics. So you might want to write that down. Correspondence principle. As mass gets large, then the quantum effects disappear. As mass gets large, the quantum effects disappear. Everything behaves classically. Okay. Also, where's the quantum number in all of these? Quantum number's here, yeah, but it's a numerator. Quantum number, in this case, up here, J, quantum number, they're all in the numerator. So correspondence principle, same thing. So there's several parts of the correspondence principle. As quantum excitation goes up, then the behavior starts to approach a classical system. So the quantum effects disappear as the excitation goes up. So the quantum number, if you have a bunch of molecules in excited states, they start to behave classically. Okay, you start to lose the quantum oddities of the wave function. If you go back to the wave function, you'll see that it starts to have a lot of curvature at really high energies, and so it looks like a classical system at really high excitation. So, and then distance or size of the molecule is in the denominator. So the box length is in the denominator. So you put a quantum system in a large container, and it behaves classically. So a gas in a room is behaving like a billiard ball. But if you squeeze a gas down into a small space, it behaves like a quantum particle. So it's very smooth. There's no quantum realm, really. There's no transition. We don't need a van full of some quantum thing like an Ant-Man and Wasp. You know, we just need to shrink the system, and there's no transition where all of a sudden it just flips, and now you're in a quantum system, whereas before you were in a classical system. It's very smooth. You just shrink the limits, the boundary conditions down, and you will start to see quantum effects emerge. Here's bond length. Again, that's sort of the size of the system, and it's in the denominator. So really long bond length, it behave just like billiard balls on a string, but you shrink that down, and then you start to see quantum effects appear. And then in here, there's really no size for the vibrational component, but it's related to this force constant. Okay, this looks like it's in the numerator, but essentially that's the force constant. A big force constant means a small L. Okay, and a small force constant means a really gradual potential, and so that would be a big L. And so it's just how that force constant's related to size of those boundary conditions. It's the same effect. So a big force constant, very huge quantum effects. Very weak force constant, more classical effects. Okay. And that's a really important part of just quantum theory applied to nature, is this correspondence principle. Now, I say there's no quantum realm. We start to see in some systems quantum effects emerge in surprising ways when we get down to the nanometer scale. And so that's why nanoscience is so interesting, is because you start to see quantum effects emerge that you can manipulate. Like you can tune the fluorescence of gold clusters in the visible region. And it's just gold. You're not changing its chemical properties, it's still gold. But the size of the gold cluster, well, you can just fine tune the fluorescence from red to green to blue. And you can create fluorescent tags using gold clusters. You don't have to find another dye or another fluorescent molecule that fluoresces in the orange region. You just need to change the size of the gold cluster, and you can move that fluorescent maximum from green right over to orange. It's really very cool. That's a nanoscience thing that's using size here to tune the fluorescent properties of gold clusters. So in the nano region, that's where some of these quantum effects start to move, but there's no sort of sharp transition. It's not like a phase transition. It just slides right into starting to see quantum effects. So that's enough for today. It's a little intro into Excel. We're going to do more with Excel this semester and with Gaussian. So next time we'll start using Gaussian too. So if you wouldn't mind putting the laptops away fairly quickly, because Dr. Norman will be here soon.